Hello and welcome to CMOS RF integrated circuits. So, we had just about started talking about the 8th module, low noise amplifiers, and I promised that before we discuss low noise amplifiers we are going to try to motivate the problem, and to motivate the problem we wanted to solve a numerical first, a numerical which was basically this. This is what we wanted to solve. We have got two blocks. The first one has a gain of 10 dB, noise figure of 2 dB. The next one has a gain of 20 dB, noise figure of 10 dB. All right. Now, we know that the combined gain is 10 dB plus 20 dB, that is 30 dB. This is the combined gain of the system. Now, what is the noise figure of this? This was the first motivating problem that I need to solve, and once I solve this we should be able to understand why I would like to design a low noise amplifier at all, okay, and also where that low noise amplifier should be, etc. So, let us now attempt to solve this problem. So, to do this, first of all you have to recall what is the definition of your noise figure. The definition of the noise figure was, suppose I have got a source over here, okay. So, the source has its noise, right, the source is inseparable from its noise. If you are talking about an antenna, the antenna has an impedance and that impedance is going to create some noise. So, we can't avoid it. Now, what is the noise contributed by the amplifier itself in relation to how much noise is coming from the source? So, that extra noise is 10 dB more than the noise of the source. So, I can model this as follows. So, I have got some noise of the source, and I will have some extra noise coming in over here, which is 10 dB more than noise of source. I am sorry, 2 dB more than the noise of the source, that is the noise figure. Okay. That will go through a gain of 10 dB. All right. Now, we have to think about the noise figure of the second building block over here. Now, the second building block has a noise figure of 10 dB. What does that mean? What does it mean when I say that the second building block has a noise figure of 10 dB? If I put a source over there, then the second building block can be modeled as something, some noise coming from the source, some noise coming from itself, which is 10 dB larger than the noise of the source. Right, and this is going to go through a gain of 20 dB, and it is coming out. So, I want to measure or I want to estimate the combined noise figure of everything taken together, right. All right. Now, let us say, let us now, instead of noise figure, let us convert these into noise factors. Noise figure is just a dB representation of noise factor. So, 2 dB is how much? So, let us say that the noise of the source is n, Okay. So, I have got n as the noise of the source, this is really a noise power. So, V n squared, okay, voltage squared, mean squared voltage, that is what we are talking about. 2 dB more than that is how much? So, you have to divide by 10. So, 10 to the power 0.2. Any ideas how much this is? This will be about a factor of 1.5. All right. Every dB is a factor of 1.25 or so. Okay. So, 1.5 times n is coming there. 10 dB is really a gain of 10, 20 dB is a gain of 100. All right. 10 dB more than the noise of the source is 10 times the noise of the source. All right. So, this is what we have got. Now, what do you think does this translate to? At the output of my system, what is the noise? So, I have got noise n plus 1.5 n, that is 2.5 n, goes through a factor of 10. So, I have got 25 n over here. I add in 10 times n. So, I have got 35 n over here. 35 n goes through a factor of 100. So, I have 3500 times n over here. Okay. But input referred, I have gone through a factor of 1000. So, it is as if I had applied 3.5 n over here and gone through my gain of 10 and my gain of 100. So, these two systems are equivalent. So, if I have a system with a noise input of 3.5 times n, it goes through a gain of 1000, I will get 3500 n at the output. And similarly, so basically these two systems are equivalent, that is it, right. So, the input referred noise is 3.5 times n. Now, your noise figure is the total input referred noise divided by the noise of the source. So, you have got 3.5 times n divided by n, which is a factor of 3.5. We have made a mistake. We have made a couple of mistakes in fact. Okay. Sorry, noise figure of 2 dB. What does this mean? That the input referred noise of the first stage is 1.5 times n. So, 1.5 times n is the input referred noise, which means 0.5 n needs to be added, n is already coming from the source. All right, this is mistake number 1. Mistake number 2 is similarly, this should be 9 times n. Okay. All right. So, with these mistakes taken into account, we will have 15 n over here, 24 n. So, I felt that the numbers were unreasonably large. So, I went back and fixed the mistakes. So, I will get 2400 n over here, and as a result this is equivalent to 2.4 times n. 2.4 times n is a factor of what? So, what is the noise figure? The noise factor is 2.4, and if you want to express it in terms of decibels, then you do 10 log of 2.4 and that will give you something like 3.5 dB. Okay. So, this whole thing will have a noise factor of 2.4. So, it is very interesting. I started off with 2 blocks, first block noise figure of 2 dB, next block noise figure of 10 dB. The noise figures do not add, I do not get 2 plus 10 equal to 12 dB of noise figure. So, this is observation number 1. So, why is this happening? So, to understand that, think of the gain of the first stage. Suppose I had a gain of 20 dB in the first stage. Suppose this was 20 dB instead of 10 dB. All right. What would happen? This new number would become 100. This would become 100. I would get 150 n over here. So, as a result I would get 159 n over here, and I would get 15900 n over there, and that would be equivalent to 1.59 times n into 100 into 100. So, my noise factor would then reduce to 1.59, right. So, if I change the gain of the first stage, if I increase the gain of the first stage, then the overall noise factor is actually dropping. So, what am I saying over here? What am I trying to say? So, you have got a system, with a certain amount of gain. This particular system has its own noise, all right. Now, whatever noise comes after this because of the subsequent systems already see an amplified signal. So, think of this. So, I have got a signal coming in, okay. Let us say the signal has an amplitude of small a, all right. Let us say the input referred noise for this is so much, let us say small n, all right. So, let us say the input referred noise for the first amplifier is small n, the amplitude of the voltage coming into the first amplifier is small a. So, you have got a signal to noise ratio of a by n at the input of the first stage. Okay. Now, what happens is you have a gain of the first stage. So, let us call this A1, right. This gain applies to both the signal as well as the noise. So, you get A times A1, you also get n times A1. So, the noise is already amplified by the first stage. Now, to this amplified noise you are adding some more noise, let us say N2, okay. You have already got amplified noise. If you add a little more noise to it, it is almost as if you are adding nothing, because the noise is already amplified. The signal is also amplified by the same factor, right. So, as a result, the overall signal to noise ratio is not going to degrade much. So, the signal to noise ratio over here is A times A1 divided by n times A1 plus N2, okay. N2 is a small quantity. Over here the signal to noise ratio is A by n. So, you can show that if A1 is large, if the gain of the first stage is large, then this is going to be approximately equal to A by n, right. So, this is something, this relationship, whatever, if you do this mathematically, if you do it with variables as opposed to numbers like we did, you come up with a formulation. That formulation is called the Freeze equation. Okay. I am not bothering to develop that formulation, it is not important at this point of time. What is important at this time is to understand that if the gain of the first stage is large, then only the noise of the first stage is important. The noise of the subsequent stages is irrelevant to me, because you know what, I am adding only small quantities of noise and the first stage already has amplified the noise of the first stage, right. So, the subsequent systems behave as if they are not producing any noise. So, I can ignore the noise produced by the subsequent systems, I just make a very good first stage. So, that is why we want to make something called a low noise amplifier. We are going to make this one beautiful amplifier that does not add much noise, okay, but amplifies. And what we are going to do is, we are going to put this low noise amplifier right after the antenna. So, your antenna is capturing some signal, the signal has some noise because of the antenna, because of everything else. The low noise amplifier is adding very little noise compared to what is already there, right. So, the low noise amplifier is adding very little noise of its own, but it is amplifying everything. So, there is noise in the source, there is signal, let us call the signal as A, okay. It is amplifying everything by a large number, let us call it capital A. So, at the output of the low noise amplifier, I am going to see A times A plus Ns times A plus N1 times A. This is the signal that I am, this is the total thing that I am going to see at the output, of which the signal to noise ratio is A times A divided by Ns times A plus N1 times A, which is equal to A by N1 plus Ns, right. So, what I am trying to do over here is I am trying to make sure that A is large, A is a large number, so that if I add further noise over here because of my subsequent systems, that further noise becomes irrelevant to me. So, if I add N 2 over here, then the total noise over there is going to be this plus N 2, and this plus N 2 is not going to make a dent in my equation because A is large. Okay. So, this is my plan. So, that is why I want to make a very good amplifier right up front, right next to the antenna. It should be a low noise amplifier. What happens if the amplifier does not amplify? What happens if the amplifier, instead of amplifying, let us say it makes the signal smaller? If it makes the signal smaller, suppose the gain of this first stage, instead of 10 dB or 20 dB, it is minus 10 dB, suppose. Okay. So, that means instead of multiplying by 100, I divide by 10. Okay. So, the overall gain is a multiplication of 100. Now, my numbers are going to change, right. Now, I have got 1.5 n over here, that is going to be divided by 10 instead of multiplied. So, I am going to get 0.15 n over here. Now, 9 n is going to be very significant compared to 0.15 n. So, I am going to get 9.15 n over here, that multiplied by 100 is going to be 915 times n, Okay. 915 times n divided by a factor of 10 means that my input was 91.5 n. Wow. So, your noise factor is now going to become equal to 91.5, which is terrible, right. So, this is what happened if I attenuated instead of amplified, right. This is really a very dramatic number. You have got 91 as opposed to 1.5 or 1.59. Right. So, your noise factor is now 91.5, which means the noise figure is almost equal to 20 dB. Right. So, this is a horrible design. So, make sure that the first stage after your antenna is the low noise amplifier. It is very important. Also, the first stage should not attenuate. Okay. As soon as you attenuate in the first stage, your entire noise characteristics is going to depend on that. All right. Subsequent stages noise is going to look larger at the input. All right. So, this is my motivation to build a low noise amplifier. A low noise amplifier does not reduce the noise that is coming from the signal. It is not possible to reduce the noise. The signal already has some noise in it, you can't get rid of that noise. What the low noise amplifier is going to do, it is that it is going to make sure that compared to the noise in the signal, it is not going to add much more noise by itself. That is all that I can do. So, the signal at the input of the low noise amplifier already has noise. What I am going to make sure is that the extra noise that I add, because I have the low noise amplifier, because I have an amplifier I am going to have some extra noise, right. That extra noise is equal to or smaller than or not a large fraction of the noise existing in the signal. So, N1 and Ns should be comparable, probably N1 should be lesser than Ns, N1 should be as small as possible. Basically, this is what a low noise amplifier means. Right. So, with this as the background motivation, we are going to start talking about strategies to make a low noise amplifier. So, before we start with the strategies to make the low noise amplifier, what are all the desirable characteristics of the low noise amplifier? Number 1, it should have a large gain. Okay. Number 2, you should have a low input referred noise. Okay, or rather low noise figure. Anything else? Anything else that comes to your mind? You are making an amplifier here. Okay. The amplifier will be made up of MOSFETs, blah blah. Okay. MOSFETs have a finite FT. You remember we talked about FT. Okay. So, you are saying large bandwidth, is it? Large bandwidth is not really an issue. Can I make a tuned low noise amplifier? If I know my signal is coming at 2 gigahertz, I am going to make sure that around 2 gigahertz I have a low noise amplifier. At DC I do not have anything. it's a strategy. So, large bandwidth is not an issue. I will just write it down and I will also point it out that this is not an issue. Linearity is an issue. You do not want your low noise amplifier to introduce distortion in the signal. Okay. What else? Anything else that comes to your mind? Think about all the topics that we have studied in this so far. Matching, right? The input impedance of the low noise amplifier should be matched to the impedance of the source, to the impedance of the antenna. So, the input impedance, you have got your low noise amplifier that looks like this. The input impedance of the low noise amplifier should be matched to the resistance of the antenna. Why? Two reasons. One is to conserve the shape of the signal and the second is to do maximum power transfer. Why would you want to do maximum power transfer? Because if you do maximum power transfer, then you are also going to get the maximum possible gain from your low noise amplifier. Am I right? If you do maximum power transfer, then you will get the maximum possible gain at the output. So, if you do maximum power transfer, then you will get the maximum possible voltage at the input of the low noise amplifier, which means that you are going to get the maximum possible output voltage of output of your low noise, total gain of the system will be maximum, right, if you have maximum possible input voltage. So, that is why you want to do maximum power transfer. Now, all this happens when you do matching, when you match the impedance of the antenna to the impedance of the low noise amplifier. All right. What about the output? Presumably the output also needs to have matching, so that you can effectively get the maximum possible gain. So, you want to do maximum power transfer as far as the output is all concerned too, right. So, as far as the output is concerned, you want to do maximum power transfer here also. So, both sides you need to do matching. Also, to conserve the shape of the signal, you would want to do matching over there. Okay. You can is this right? What was the maximum power transfer theorem? The maximum power transfer theorem was, if you have control, if you do not have control over the source resistance, so RS is part of V and you can do nothing about it, all right. So, the maximum power transfer theorem was that if RL is equal to RS conjugate, in the general case, if RL is equal to RS conjugate, then I am going to get maximum power transfer. All right, and maximum gain as a result. So, this happens only when I say that RS is part of the voltage source that we are seeing, but when I am talking about the LNA output, here I have direct control over what the RS is. So, RS equal to 0 will give me the best gain, right. If I can make RS as small as possible, then I can get highest possible gain given a load. So, in that sense it is not really clear that you have to do the output matching over there. Output matching will be necessary to conserve the shape of the signal in any case, right. Also the optimum you can keep decreasing the output impedance of the LNA, your gain is going to marginally keep increasing, but really do you want to spend so much in decreasing the output impedance of the LNA to 0? You probably do not want to spend so much. The marginal benefit that you get is probably not worth it. So, in that case the optimum point would be to set your output impedance of the LNA equal to the input impedance of the next stage or conjugate of the input impedance of the next stage. So, that is why you want to do output matching. All right. So, we unfortunately are going to start with matching. All right, we are not going to go by the serial number when we are going to discuss the low noise amplifier. Okay. We are going to start with matching. How can we match the input impedance of our amplifier to the antenna, to the resistance of the antenna? So, the antenna is resistive or mostly resistive. All right. I want the input impedance of the low noise amplifier to be equal to R 0 at the chosen frequency, where the low noise amplifier is going to operate. How can I do this? First of all, if you think of what you studied in your matching earlier, long back when we did matching, probably initial part of this course, we had a matching network. This matching network was made up of inductors and capacitors. That was it, okay, maybe mutual inductances, but mostly inductors and capacitors. And what I was doing was, if I have a resistance over here, then I was able to match it to an arbitrary source resistance. All right. So, I have to choose what kind of whether the impedance transformation is going to go upwards or downwards, and accordingly I would have to either choose the L shape in a certain fashion, right. So, I would either have to have a series L and RL, or I would have to have a shunt L and RL, and accordingly I would figure out what the matching network needs to be. Now, the key over here that I want you to understand is that the load that you are delivering power to has got to be resistive. If you do not have a resistive load, then you can't possibly do matching. If this load over here is not resistive at all, if it was a resistor in shunt with a capacitor, I can do it. I can do matching. I basically need to put an inductor in shunt with the capacitor to tune out the capacitor, right. Resistor in series with capacitor, I can do it. But if it is only a capacitor, is it possible to do it? Can I do maximum power transfer onto a capacitor? No, because a capacitor by definition is not going to consume any power at all, right. So, it is not possible to do matching when the load is a pure capacitor or a pure inductor. There has to be some resistive component in the load. Now, our load over here, I mean what are you trying to drive over here? What we are trying to drive is the gate of a MOSFET, probably the gate of a MOSFET. What does the gate of a MOSFET look like? It looks like a capacitor. Is there any resistance? There is probably some gate resistance, you are right, there is probably some little bit of gate resistance associated with the polysilicon, right. However, mostly it is a capacitor that you are trying to drive. Okay. It is conceivable to do maximum power transfer onto that gate resistance and then proceed. But let us say to first order there is no gate resistance. Okay. To your first order gate resistance is 0, the input impedance of the MOSFET is a pure capacitor. What do you do in that case? How are you going to tackle this? How are you going to do matching? It is not possible to do matching in under such a scenario, right. You need something that dissipates power, otherwise you have not got the maximum voltage at the input. If you have not got the maximum voltage at the input, then you are not going to achieve the maximum possible gain from your circuit. So, how are we going to tackle this problem? I need suggestions. So, the first suggestion is the obvious, let us put a resistor over there, right. This is going to sort out my matching issue. I do not even need a matching network over there, or even if I do put a matching network, it is just to tune out the CGS of the capacitance, MOS capacitance, right. Just to get rid of all that, I probably need to put an inductor in shunt, etc. Fine. So, let us safely ignore the capacitance contributed by the MOSFET, by the gate of the MOSFET, CGS, CGD, etc., etc. So, all that has been taken care of by the matching network. So, I have got RS and presumably you are going to put another RS over here and you are going to get beautiful matching, and this should work, right. So, under your list of objectives, your let us call this the zeroth cut design. Okay. So, your zeroth cut design, I have not designed the complete thing, but input matching I have achieved. Okay. So, presumably I will work on the design further and I will get a good gain. I will I will do whatever needs to be done to get good linearity, etc. But a low noise amplifier needs to have a low noise figure. What is the noise figure of this? What is the minimum noise figure offered by this low noise amplifier? So, I want to compute the noise figure of this particular low noise amplifier. do not think about the MOSFET etc., those are only going to add to the noise figure further. Okay. Just the fact that I have got RS over here means that my noise figure, noise factor is how much. So, whatever noise is coming from the antenna, RS is contributing equal amount of noise, this particular RS is contributing equal amount of noise. So, my noise factor should be at least 2. Okay. On top of it, there is the MOSFET, which has its own noise. I did not even bother about the MOSFET, right. So, just by looking at the circuit, you can say that this has a noise factor at least of 2, which means a noise figure of 3 dB. Now, in the world of low noise amplifiers, a noise figure of 3 dB is not competitive. Okay. Every 0.1 dB of noise figure counts, all right. And if you produce a low noise amplifier of noise figure 3 dB, people are going to laugh at you, right. Every 0.1 dB of noise figure is very, very important. So, this is just not good enough. This is not going to make it to production. Your boss is going to laugh at you if you make this circuit, right. You want noise figure to be something like a good number is 1 dB, 1.2 dB, 1.5 dB, 2 dB, right. 3 dB is a bad design, and that too 3 dB without even considering what else is there. So, the MOSFET did not even come into the picture, I am already at 3 dB. So, once I put the MOSFET there, it is going to go up 4 dB, 5 dB, something like that, this is going to be, right. So, this kind of a low noise amplifier is not competitive because of a horrible noise figure. So, my zeroth cut design, where I did matching, but I did nothing else, did not really work. I can't work as a low noise amplifier. Okay. So, then we are back to square one. I have got a system I am willing to put a matching network in between, and I need an amplifier, but the input impedance of the amplifier should have a resistive component. I like the gate of the MOSFET to be an amplifier, but the input impedance of that is not resistive at all, it's in fact it is capacitive. So, what do I do? So, one thought is that maybe we are making a mistake by putting the gate over there, maybe the gate is not necessary. We know other structures of amplifiers, we do not need to put the gate all the time. Yeah. Why do not we do the common gate amplifier? Can we do the common gate amplifier instead of what we were doing earlier? This is feasible. In fact, this can be done. Next possibility is, why are you thinking that the input is only going to be connected to the gate? What about my beautiful shunt series amplifier? Okay. This could have a resistive component as its input impedance. So, this is definitely a strategy. In fact, to get maximum gain you want to avoid this resistance altogether. Okay. This is definitely a strategy, and people make these amplifiers as low noise amplifiers. You can do your matching. The problem with this kind of a design is that you are using a resistor over here, and a resistor contributes noise, creates noise, all right. And in general a resistor is something which is avoidable if you are talking about a low noise amplifier. So, you would like, would rather not put a resistor over there. So, this is a possible design. Okay. It is used in fact in a lot of low noise amplifiers, especially at the inputs of oscilloscopes. This is what is done, or if you are talking about active probes, this is what is done, right. However, the problem over here is that the low noise could have been lower if the resistor was avoided. All right. This is so far so good. Are we proceeding systematically? So, this is also a possible design. Okay. There are problems with this also. The problem with this is that the channel noise which comes in shunt with the channel noise is also proportional to GM of the device. This particular channel noise is going to go into the source resistance directly, right, which means that your total noise, input referred noise, is going to become proportional to GM. Okay, this is not something which is very desirable. Okay, this is not something very desirable. If I increase GM, you saw, right, in the previous lectures you saw that the gate referred noise of the MOSFET was 8 by 3 kT divided by GM. What does this mean? This means that if I make a device with a large GM, the noise, gate referred noise, is actually going to drop. Okay. Channel current noise is increasing, but it is as if I applied a lower voltage, lower noise voltage at the gate. So, it is not desirable to have something which is proportional to GM. That means that at high frequencies, when I need large GM, I will get a lot of noise from the MOSFET itself. Okay. So far so good. Now, so after all this, what we do? What do we do? What is an acceptable design? So, anything is acceptable as long as the noise figure is low. This is the catchword. Now, one of the interesting strategies that people use is they put an inductor and degenerate the source. So, what I am going to do as a first cut is I am going to try to find out the input impedance of this particular structure. All right. So, let us try to find out the input impedance of this. To work out the input impedance of this, what do you have to do? You have to apply a voltage source and you have to see what is the current going in. Okay. And you have to replace the MOSFET with its small signal model. All right, these are all the different components. So, I am going to redraw this. All right. So, this is my redrawing of that. CDB became irrelevant as a result, and the next thing I am going to do is I am going to lump L, CSB and RDS into one combined element called Z. Okay, which is the parallel combination of all this, and you keep this thing in your scratch pad. So, this is Z. All right. So, this is a significantly simplified drawing of my system. I have applied V volts over here. So, CGD is basically just going to come in parallel with everything else. So, if I find the input impedance without CGD, the final input impedance will be CGD in shunt with whatever I have found. So, CGD also is not particularly important. All right. So, this is what we are going to do. This is the system we are going to analyze for now. So, I have applied V over here, and then you have to work out a Kirchhoff's node equation. Let us say this is V s. So, let us say I have applied V g, this is V s. So, therefore, if I work on Kirchhoff's node equation, I get j omega CGS times VGS, that is the current going through CGS, plus GM times VGS, and that is equal to Z Vs by Z. Okay. So, we are going to solve this equation and find out Vs, right. So, you put all the Vs's together, all the Vg's together. So, you have got Vg times j omega CGS plus Gm is equal to Vs times 1 by Z minus Gm minus plus Gm plus j omega CGS, and as a result Vs is Vg times j omega CGS plus Gm divided by j omega CGS plus Gm plus 1 by Z. Now, we have found out what is Vs, and therefore, we can find out the input current, right. All right, we are going to stop here. Next class we are going to continue from this point. We actually are leaving it at a rather interesting juncture. It will be good if you just solve it, you will see that something interesting pops out, and try to see what can be done further. So, I am going to leave this on this note, that you continue with this analysis, try to figure out what pops out, and then in the next class we are going to give I am going to give my interpretation of what is popping out. All right. So, with this I am going to close this lecture. Thanks.